real men watch and happy to Disney later. Oh, like, Snap? No. What's the one guy? Popular MMOs.
Okay, let's get started.
Yeah.
Well, happy Friday. How are you all doing?
Amazing. Okay. Good.
Good. I just want to say I heard that you guys are doing really well on your pre-lab quizzes and lab reports, so I'm very happy for that. Keep up the good work. If you have any questions, concerns, make sure you talk to us, okay? All right. So I believe next Friday you have a quiz. Okay, that's good. Um, just remember when you study, after you study, it would be a good idea to kind of practice last year's quiz. So last year's quiz is posted without the key and with the key. And after you study, just try to solve it before you look at the key. And if your answers are close to the key, then you're ready. The questions won't be the same, obviously, but will be similar style. And then don't be too alarmed when you see the key is detailed. Usually my key is very thorough, detailed, trying to cover every possible answer, every possible way a student can answer, but sometimes it's not that much detail, and try to stay within the space I give you for every short answer. So don't get too alarmed by the thoroughness of my key. All right, it's for you to study. Okay. Any questions? Yes, Emma.
What is the quiz now? They're gonna be like 20 minutes, like they give you in class.
Yeah, it will be at the beginning of the class, 15 to 20 minutes. Usually you can finish it in 15 minutes, but I give 20, 25 minutes for it to be done at the beginning so that you get it over with before we continue with the lecture. Yeah. Yeah. Any other questions? And everything will be on the quiz up to Wednesday's lecture. So start studying this weekend. Just start to get a lot of that material out of your way. Okay. All right. Anything else? Okay. Well, I didn't go too far. We were casually talking about chromatography last time I was lecturing, and then Gary came and talked to you about GC. So I will just continue with principles of chromatography, and a lot of what I talk about is mostly relevant to liquid chromatography. So, but let's just go back and tell me in one word, what does chromatography mean to you? Or what does it do? One word. You said it was separation. Yes. So the first thing when we do chromatography, if we have a mixture of components, the first thing we want to do is separate them. If our chromatographic technique doesn't separate our mixed components, we cannot identify and we cannot quantify. Okay, so the first step in chromatography is separation. So we're going to learn about different modes of separation as we talk about chromatography. You learned about gas chromatography, but in liquid chromatography, there are different modes of separation. So we're going to talk about that to achieve separation, then detection of the compounds. Then we identify what these compounds are. And if we have standards, we quantify. Okay, so kind of that's the series of events in chromatographic analysis. I don't expect you to know much about chromatography, and if you know, that would be great. Have you had any chromatography in any place? Where?
At my job, I was trained on HPLC.
Oh, very good. And any other like courses you talked about chromatography? Yeah, where?
In Oaken Lab.
Oh, okay, very good. So some of you have been exposed to chromatography. We're going to spend probably the remaining not remaining, the next 3 to 4 lectures, finishing up chromatography. Okay, so in order for components to separate, they need to interact with your chromatographic material. So in that form of molecular interaction can be adsorptive chromatography is one of them. And what form of intermolecular interaction can take place in adsorptive chromatography? Guess. You have a component or components, and then you have your chromatographic phase. How would they interact with each other? They have to interact in order for components to separate, and every component have different strengths of interaction with the column. If you remember the justice example, 3 of us went into that store, but each one of us interacted differently with the components in the store. Okay, so any guess? Just, when in doubt, you go with all of them. The point of this question is interactions are not covalent. In chromatography, you do not have component and chromatographic phase covalent interaction, because covalent interaction is strong interaction. You want your components to interact, but you don't want them to stick to the chromatographic phase and not come out of your column or of your paper or thin layer chromatography. So they all non-covalent interactions can take place in adsorptive chromatography, and we'll talk about that later. Okay. Have you heard of the term reverse phase or reversed phase? It's okay if you have not. We're going to learn about it, okay? We're going to learn about reversed phase and normal phase chromatography. These are very, very common chromatography in liquid chromatography. So in reverse phase or reversed phase, you can see it both ways, with a D or without a D. So usually you have a phase that is nonpolar interacting with nonpolar or relatively nonpolar components. So, and then the polar components don't like to interact. So if the justice is a reversed phase chromatography, the justice store, I'm a polar component. I will not interact with the column, with the column or the store. I would go in and out. So polar components will elute first or leave first. Nonpolar components will actually elute last. The more nonpolar the components are, they will interact the most with the column or the stationary phase or the chromatographic phase and leave last. And if the chromatographic phase is nonpolar, the mobile phase will be relatively polar. So in this case, A and C are are the correct answers. So that would be F. And then don't worry, we're going to explain this more when we get to it, just to see how much you know. So I'm going to give you a little bit of a historic perspective. I know Gary did a little bit of that for the GC, but way back when, in the late 1800s, I would say, David Day, an American geologist, separated crude petroleum with fuller earth. So that is kind of the first application of chromatography, but he was not credited for this, and it wasn't that separation that gave chromatography its name. Actually, Mikhail Svet, the one that separated leaf pigments, and he used chalk to separate those. He had a column and packed it with chalk and separated the leaf pigments into different colors. And that's where the name chromatography came from chroma, from color, because we separated leaf pigments. And he was the one that was credited for the discovery of chromatography. And then it kind of didn't get much attention until the 1940s, and that's when partition chromatography and paper chromatography, both are liquid chromatography, started to become popular. And we'll talk about partition chromatography here in a little bit. And in the 60s, gas chromatography started to take attention and boomed because of the petroleum industry and separation of petroleum or fuel, basically. And it kind of, the technology advanced very quickly before the liquid chromatography started to advance as much. That's kind of the history. So let's talk about uses. How can we use chromatography? And what types of analysis? Can you give an example? So Ali, you said you did that in your work. What were you analyzing?
The concentration of potassium sorbate in potatoes.
Potassium sorbate in potatoes. You used HPLC to determine that. Very good. What other applications you can think of or uses for chromatography? Whatever you say is going to be right.
Flavor.
Flavor. Thank you. Yes. So Gary talked about gas chromatography, which is very commonly used for flavor analysis. What else can you think of? Like I said, you can name anything and it will be correct. Yes, protein. We can use it in separation of proteins, definitely. Separation of amino acids for determining amino acid composition. Separation of sugars and oligosaccharides to determine the quantities of these different components. We can use it for pesticides, separation and identification of pesticides. We can use it for vitamins, organic acids, fatty acids. You're going to be using gas chromatography in the next couple of weeks in lab to determine fatty acid composition. So many uses. Antioxidants, for example, is also can be used with chromatography. We're going to talk about the principles of chromatography, but a lot of the following chapters, when we talk about different components analysis, we'll go back and say, okay, and this is done by reverse phase, or this is done by hydrophobic interaction chromatography, or this is done by gas chromatography. So now we're going to talk about principles, but then later on in the semester, once you are very strong with these principles, we're going to learn different applications. Okay. Very good. So the chromatography is based on a principle that is the extraction principle. In extraction, usually you have two liquid phases and you put your components or sample, whatever you're analyzing or trying to extract, in these two phases, and then you mix, and these two phases will separate, and your component that would like more phase than the other will be concentrated in that particular phase. So for example, actual means of analysis, we extract fat using organic solvents to determine fat content. So that is that you're going to learn about a method called Mojonian or Mojiner, and I mentioned it multiple times. So there's aqueous phase, and then there's the organic phase, and there's your sample. And you're going to mix, and then your fat layer will be concentrated in the organic phase. So you're extracting that fat from your sample and then quantifying it. So that is used, so this extraction is used as actual means of analysis. Preliminary sample cleanup. And I'm also going to give an example where we defat before carbohydrate analysis. So if you have a sample, let's say oat flour, and oat has 7% 7% fat, 6 to 7% fat. But you want to determine the sugars and oligosaccharides in your oat flour, you have to defat first. So it's kind of a preliminary cleanup step before you dive into particular analysis. That's just an example. And then sometimes your components of interest are present in a very, very small amount, like flavors. So we really have to take them out and concentrate them separately from other components so that we can analyze them. So the reason I mention extraction, because I'm going to talk about how partition chromatography came to be. But before I talk about that, this is an example of batch extraction. You're all familiar with the separatory funnel, where two immiscible solvents are put together, and then the components of your sample are separated based on their affinity to these two phases. And then there is continuous or semi-continuous extraction. This is a Soxhlet unit that you will learn about in the fat analysis lab, where we also extract the fat by putting a solvent here, organic solvent that will evaporate, go up into a condenser, and comes down to where we have our sample, solubilize the fat, and siphons back into the original flask. So that is, well, it is actually a semi-continuous extraction. But what I want to talk about is countercurrent extraction. And that is the basis for partition chromatography. So in countercurrent extraction, what happens is that you have two phases, phase 1 and phase 2. And phase 2 is the phase that called stationary phase. That means it doesn't move. Stationary, it doesn't move. It stays where you put it. And then phase 1 is your mobile phase, the phase that moves, basically. And then at equilibrium, when you mix and let it equilibrate, the compound will reach something called partition coefficient, which is a constant. So in that partition coefficient is the concentration of this solute or component in your sample in phase 1 over the concentration of it in phase 2. So if solute A is more soluble in phase 2, it would like to interact with your stationary phase, whereas solute B is more soluble in the mobile phase. That means that solute A has less K than solute B, meaning because solute A likes to interact in phase 2, so the concentration of at equilibrium of this solute A will be higher in phase 2 and lower in phase 1. So K will be low compared to B, that the concentration will be higher in phase 1 and lower in phase 2. That's what it means. Now, if I want to apply it to separation, so I used to have a link that works, and now for some reason the link is broken. It really demonstrated very well how the countercurrent extraction works. So if you can see, you have tubes in a row. So this represents tubes in a row. And what happens, I'm going to draw it because the link doesn't work anymore. To explain countercurrent extraction and partition chromatography. So from countercurrent extraction, partition chromatography was developed. Let me explain. So I'm just going to draw, for simplicity, about, let's say, 5 tubes. Okay. So, of course, the more tubes you have, the more separation you're going to get. It's like, I don't know if Gary talked about shorter column versus longer column. The longer column you have, the better separation or resolution. Resolution is separation of two peaks from each other. The more separation you have. But let's not worry about that right now. Let me demonstrate. So you put your phase 2 first, which is the stationary phase. So I'm just going to call it 2 phase tubes, and that's your stationary phase. So you put your first liquid, whatever that phase is, doesn't matter at this point. You just put it there. That's your stationary phase. That means it remains in this tube. And then what you have, you put your phase one, which will be the one that will transfer to each tube. And then you have your sample or solutes, A and B in this case. So you put the second phase, the second solvent, phase one in this case. And then you have A and you have B. So A was given a K value of 0.5 and B had a K value of 3.5. This means that B likes phase one more and A likes phase two more, if you remember the equation on your previous slide. So the equation is of K is concentration in phase one over concentration in phase two, so that you have everything in one place. So B is higher. So this means it likes the moving phase, the mobile phase. So when I put shake, everything will shake. This using that shaker tube goes back and forth. And then you let it settle, reach equilibrium. And then this will move to here. So now I have A and B here and A and B here. But where do I have more B? Up here or up down here? Based on everything I said. Where do you have higher concentration of B? Up here or down here? Oh. On the top. Yes. Because it likes phase one better. Then another shake happens. So shake, 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 and then transfer. And again, I have now, I'm gonna draw this smaller because now we know that we have more B here. And the more I move, shake, and reach equilibrium and separate, the bigger the B, the smaller the A here, and then gradually you won't have any more B at the bottom. So what does that mean in chromatographic separation? So if you look at the chromatogram, then what happens is initially you have A and B together. And then we will start seeing B coming out, and then A will follow. So B will come out first, and then A will follow. And this is a response. So it could be an absorption, it could be an FID response, flame ionization detector response for doing TC. It could be any type of a response you get from your detector. Refractive index. So you will get a response here, and this is time. So basically what happens is you are separating them more and more and more. With every equilibrium you get and transfer, you get this separated. Okay. So you get two peaks. And B will come first, A will come later, because B liked the mobile phase more than the stationary phase. So it will come out first. Okay, you want me to keep it? It's an important concept because this is how partition chromatography came to be based on this kind of countercurrent structure. So what's the main theme here? We're trying to achieve separation. We're trying to achieve separation based on how much A and B are different in their liking of the two phases. If they like the phases, if they have the same K, you can never separate. You have to use a different set of solvents or chromatographic phases. Because if they have the same affinity to these phases you are using, they cannot be separated. So that's why we have different types of chromatography to ensure that components, we figure out a way to separate them. They don't like everything the same way. Okay, does that make sense to you? Okay, all right. So there are certain terminologies that we will be using, and I want you to be familiar with these terminologies. So when I say solute, I mean a component that is soluble in a particular solvent. So oftentimes chromatographic terminology will say we're separating different solutes that are soluble in water, soluble in methanol, or whatever is the solvent. So we call them solutes. Stationary phase, meaning the phase that doesn't move. In this case, here, the phase 2 does not move. All right, stationary. And it could be liquid, it could be solid. And I'll give examples when the stationary phase is liquid and when the stationary phase is solid. The mobile phase, meaning the phase that moves. And in this case, phase 1 is the phase that moves. When you shake and transfer, that is the one that moves in that countercurrent extraction. But in chromatography, the mobile phase could be in gas chromatography is the gas that Gary talked about, is the mobile phase that carries the components and allow them to interact with the stationary phase. And then series of equilibration. So like that countercurrent, so every time they shake, they let it settle until we reach equilibrium. So in a column chromatography, also we have a series of equilibrium. They're not visible to us like the tubes, but there are certain number of equilibrium that happens in every column during the separation. So we're going to talk about series of equilibration later on when we talk about resolution or separation principle. So eluent, so is what we're using to help those components move. And then the elute is the verb of it. So the component could sometimes we call it eluent or coming out, the solute that is coming out. And then the elute is the verb we use. Instead of saying moving or coming out, we say eluting. We use the verb elute. And a chromatographic peak, this is a chromatographic peak, and usually it's based on the response over time. So if we're measuring absorption at a particular wavelength, so that would be the absorption that we measure at each increment of time. Yeah, so it depends on the detector we have and what the response is. We plot the response against time, we get a chromatographic peak. And when I will talk later about how that peak comes when we talk more about a column, but I'll briefly mention it here. And then I'll talk about it more later. So if you have a column, which we always gonna be talking more about a column chromatography. So you have a column, you have your stationary phase here, and then you inject your sample. It will start as one single layer on the chromatographic column, and then you have your mobile phase going on. Here, this is your sample that has different components, A, B, C, etc. And then this is your stationary phase. So as this sample goes through the column, you start having spread and separation. So A, B, C. So they start all together and then they interact with your stationary phase. C is interacting the least, that's why it's moving the fastest. But also there is diffusion. So there is movement with the mobile phase down. We call it in and out movement with the mobile phase. And then you have a diffusion within the column. So that's why as they come out, they will start coming out because they diffused, you will have a peak. If there is no diffusion, it will be just a line, but that doesn't usually happen. You always have kind of a peak. So this would be a peak. Concentrate, this is the highest concentration. So the diffusion within the column caused them to spread out and not come out at 1 second together. They come out over a few seconds. And that's what gives us this shape of a chromatograph. But I'll talk about it more later. But since I brought it up, what a chromatographic peak is, that's what it is. When they separate, they spread out, and then they come out in a form of a peak, chromatographic peak. Okay. So chromatography, like I said, is a separation technique used a lot in food analysis. We'll give a lot of examples later. And it is based on partitioning between two phases or distribution between two phases. If it's a liquid and liquid, so if you have a liquid stationary phase and liquid mobile phase, we call it partitioning between two phases. If one of the phases, the stationary phase, is solid, we call it distribution. Okay. So you either have a partition coefficient or you have a distribution coefficient. Partition is when the two phases are liquid. Okay. You can stop me anytime to ask, to clarify, okay? Don't forget that. And you're not expected to know all this, so questions are expected. If you don't ask, that means you're all good. Are you all good? Oh. All right, so we have 3 types of chromatography. So when I ask you in an exam, I want to separate flavor components. Which type of chromatography should I use? Then I expect you to tell me gas chromatography or liquid chromatography. That's what I'm asking. So if I say flavor, you would go, Gary talked about gas chromatography. Flavor components are volatile, so they're going to move in a gaseous phase. So the type of chromatography is gas chromatography. So we have 3 types of chromatography. Gas chromatography, supercritical fluid chromatography, and I'll talk about that later. And then we have liquid chromatography. Now, most common is gas chromatography and gas chromatography and liquid chromatography. Supercritical fluid chromatography is used, but it's not very common. So in liquid chromatography, we have planar chromatography or column chromatography. So planar chromatography, meaning it's on a plane, so paper or thin layer chromatography. I'll talk about them. Paper chromatography is not very much used anymore, maybe only in the laboratory when you are separating amino acids in a lab, right? You've done that in organic chem lab, yes. And then thin layer chromatography is still used for screening purposes, not necessarily for accurate quantification, but column chromatography is the most commonly used chromatography under liquid chromatography. Of course, gas chromatography is column chromatography. Okay, so when we say gas chromatography or liquid chromatography, the gas and the liquid is telling us about the mobile phase. So the moving phase. In gas chromatography, your mobile phase or the moving phase is gas. Probably Gary talked about helium as a carrier gas. Okay. In liquid chromatography, your mobile phase is always liquid. It could be water, it could be methanol, it could be acetonitrile, it could be a buffer, it could be a combination. Now, the stationary phase in gas chromatography originally used to be solid. More modern, they have liquid bound to a solid, which is kind of like a support. The solid is a support, and the liquid bound to that support is your stationary phase. So it's bound to a support, so it's stationary, it doesn't move. In liquid chromatography, you can also have a liquid bound to a solid support. So liquid-liquid, which is partition chromatography in this case. Both paper and thin layer chromatography, it is liquid-liquid because paper and silica, mostly in thin layer chromatography, act as just a support. And then it gets impregnated with water, for example. And then water becomes your stationary phase. So that's why the planar chromatography is always liquid-liquid. And we always talk about partition in this case. Column chromatography can be liquid-solid, where the solid is your stationary phase, or solid is a support and the liquid is bound to that solid and it becomes liquid-liquid chromatography. This is very common also in column chromatography. Okay, so that's kind of like general right now. And if we want to go a little bit into specific, and then I wanted to talk about, if I say, what's the mode of separation? So I asked you about a type, and then I asked you about mode of separation. So type of chromatography, and then I say, what's the mode of separation? Then we dive into, for liquid chromatography, column liquid chromatography, it can be size exclusion, meaning separation only based on size, and we will talk about that. Molecular size. There is no chemical interactions, just filtering through, separating by size. That's the mode of separation. If we say partition chromatography, well, there are two modes. We're going to talk about reversed phase, and we're going to talk about normal phase. These are two different modes of separation in partition. Under solid, liquid solid, we have so many. We have hydrophilic interactions. So your components are interacting with a solid phase by hydrophilic interaction, like polar type of interactions. And then we have hydrophobic interactions where you are or not you, the components are interacting with the stationary phase via hydrophobic types of interaction. Then we have ion exchange. That's the most complex, I would say, in terms of mode of separation, because under ion exchange, we have anion and cation. What does that mean to you? When you hear anion exchange, What does that mean to you? From the term anion. Yes, so negative. So your components that are negatively charged, you are separating based on their charge density, but they're negatively charged. So they will be interacting with the stationary phase that has positive charges. So ion exchange is the interaction is electrostatic, so ionic electrostatic interaction. So we are either separating negatively charged, we call it anion exchange, we're exchanging, the ions are exchanging between the stationary phase and the mobile phase, and they are negatively charged. Or it could be cation exchange, meaning your ions are positively charged, so your positive ions are exchanging between a stationary phase that is negatively charged, because electrostatic interactions, ionic interaction, positive interact with negative. Okay. So cations, meaning your charges if your molecules are positive and they are interacting with a negative charge. Right? Let me draw that because I will talk about it more later, but I want you to start deciphering that by the time we get to it. It becomes an easier concept. So if you have positive charges, so meaning your compounds that you're trying, or your solutes that you're trying to separate, they carry charges, positive. So one has 3 net positive charge, one has 2, one has 1. And then you have your stationary phase. If you want it to interact, that's how you separate. If you don't interact with the column, they're not going to separate. The first thing you want is your components to interact with your column. So the column has negative charges attached to your stationary phase. So then they are going to be interacting, exchanging between your mobile phase and these compounds are going to be interacting with your column. The one that has the most positive charge will interact the most, and the one that has the least positive charge will interact the least, and then will leave first. So this is a form of cation or anion exchange. Huh? Anion. That is why we are going to continue to talk about it, because it's very confusing and you are exchanging positively charged. So the exchange is the positive components are going back and forth between the stationary phase and the mobile. So if you're exchanging positive charge, what is it called? Cation. So the naming does not follow the column. The naming follows the components that you're trying to separate. And that's the most confusing part of ion exchange, is remembering the naming follows what? What am I exchanging between phase, the stationary phase and the mobile phase? What's being exchanged are my positively charged ions, so it's cation, right? Okay. All right, but we'll talk much more about that. And then we have affinity chromatography. And from its name, so the components have a specific affinity to your stationary phase, your column. So very, very specific, like key and lock. So it's like enzyme and substrate, or antibodies and antigens. Very specific type of interaction. And we'll talk more about. I had a question? No. Okay. All right. So this is an important study table, table 12.1 in your book. It's very important because it kind of summarizes what you really want to know about different methods. So gas liquid chromatography, that means your mobile phase is gas, your stationary phase is liquid. Gas solid chromatography, meaning your gas is the mobile phase and solid is the stationary phase. Normal phase chromatography, just giving you an example, your mobile phase is non-polar liquid, and the stationary phase is polar liquid or solid. Okay, and so on. And then here, retention varies with. So let me define the word retention. What does it mean to you when you hear the word retention as it relates to your solute and your stationary phase? You want to give it a go?
Time.
Yeah, the time it takes, how, yeah, it's retention, this meaning the staying on the on the chromatographic phase or stationary phase. So the time it stayed on that phase, okay? How long it stayed. So what impacts retention? That means retention on your column, retention on the stationary phase. What each method, what impacts retention. For gas chromatography, I know Gary talked about molecular weight matters, polarity matters, a boiling point, because you want them to get into the gaseous phase and get into your carrying gas. So every component have a different boiling point. So you can separate them based on their boiling point, which is impacted by molecular weight, which is impacted also by whether or not the polarity or the relative polarity. Okay, so let's say, let's talk about size exclusion. Easy. So they're separated based on molecular size. So the retention, how long they stay on the column, is based on how big or how small they are. Okay. Questions? All right. Okay. You already talked about gas chromatography with Gary, so just a quick overview. Do you want to explain to me what you're seeing here? Where is your carrier gas? What is your carrier gas? On the left. Yes. That's helium in this chromatogram. So that's your carrier gas. So that's your mobile phase. All right. So why do we have the column in an oven? Why do we need high temperature? Yes, yes, because you want them to be in the gaseous state, your components, so that they can move along with your helium. All right, so there you build something called temperature gradient. Okay, so you have a column, very, very long column. You'll see it in lab or next week and the week after. It's a very, very long column, and it's kind of like a coil capillary column. And the temperature, you build the gradient, and the components interact with your column. You have different types of material that is filled in the column. So your components will interact based how much they like the column material. And then you have a gradient to force them into the gaseous state. And the ones with the lower boiling point will evaporate first and move quicker through the column and reach the detector first. Okay, in this example, the detector is flame ionization detector because you have a hydrogen gas and an oxygen source to form a flame. And Gary talked about FID, and this is the detector that you're going to be using in lab. So the FID, so what happens is where your organic components reach the detector, the FID detector, so there's flame, so the organic component becomes ions. So they get ionized by the flame, and then there would be a potential or a current run through, and then each ion will have a different response, which is the change in the potential or change in the current. And that's the response over time. And then you get your peak. So every component will have a different response. So you will learn more about FID in lab and how we're going to use it to identify fatty acids in your different oil samples. So it will be a major component of your lab. And if you get the question in the quiz or exam, most of the time I'll be asking about FID because it's the most common detector used in gas chromatography. I know Gary talked about so many different detectors, but for organic compounds, FID is what is used. All right, so I think we got to the end of the lecture, and I'll see you on Monday. Have a great weekend, you guys.
Where are you going?